Hello everyone, welcome to Rate Forecasting System. My name is Mariam. I'm a member of Fortune Teller team with Wahid, Nasrin and Homayun. In this developing world, natural systems are increasingly strained and under threat. The future is uncertain as the COVID-19 pandemic has made tangible for so many hazardous events that may have been thought of restricted just to one sector or spatially and temporally limited can quickly transform into crisis with long-lasting and globally catastrophic consequences. Scientists warn about drought and its severe, wide-ranging and cascading impacts. Water deficit affects production, sales, and business in a variety of sectors. Other impacts like human health, farming and livestock, even tourism and power generation. In 2011, USA has been hit by its worst drought in half a century, causing a fast drop in crop yields. Corn and soybeans prices are on the rise as a result. As the USA made up 33% of world soybean production, soybean prices has increased by 24.3% to $464 per metric per ton. Social impacts of drought are ways that affects people's health and safety. Examples of social impacts are economic losses, smaller bread basket, water wars, and low water quality. Natural disasters cost about $18 billion a year. According to a research in climate-smart economies, for every dollar invested in resilient infrastructure, $4 in benefits are generated. Also, it's estimated that an earlier response to drought in some countries in Africa would have saved $1.6 billion in humanitarian response. Climate change solutions and products are commercially viable with market share. This market is estimated to account for more than $8,000 million by the end of 2028. End users and stakeholders of these markets are governments, environmental organizations, farmers, policymakers, and so on. In 2015, 17 global goals were set up by the United Nations. It's a collection of 17 interlinked global goals designed to be a blueprint for achieving a better and more sustainable future for all. These 17 goals are intended to be achieved by the year 2030. And a call for action by all countries around the world. Goal number 13 is to take urgent action to combat climate change and its impacts. Drought negatively affects the achievement of these global agreements, so its risk reduction should be at the heart of any accelerating action. Our drought forecasting system would definitely match and meet reaching this goal. Another one is an important approach to drought risk management. This plan has 10 steps that helps policymakers to identify drought and develop solutions. Step 5 of this plan focuses on writing key tenets of national drought management and has 4 elements. Our rate forecasting system covers needs of all these 4 elements: drought monitoring, drought forecasting, locating drought vulnerable areas, and observe drought impacts through reporting. Here, we talk about some industry solutions that are developed around the world by organizations for drought monitoring. Dry Danube is the drought monitoring tool for the entire Danube region. Global Drought Observatory, its focus is on a map viewer and a report. Disaster Alert, a mobile app that offers updates about 18 different types of active hazards like hurricanes, floods, and also drought. There are 3 main drawbacks for these systems. None of them has drought forecasting, only some monitoring maps and reports of current weather. Next drawback is no risk management is applied, and none of them has the ability to integrate with the decision process. So we get to our solution. Our project plan is to develop a risk-adjusted and AI-based forecasting system. AI is an increasingly important tool in weather prediction because we are able to analyze large amounts of meteorological data and discover complex and intricate relations among these data. This helps us to respond to challenging new demands in weather forecasting. We built drought monitoring and early warning system. By forecasting drought levels using appropriate drought indicators, there will be a warning signal and sharing arrangement to adopt climate-smart economy. This will warn local communities, government decision makers, and meteorologists when there's a risk of drought. Our project has social values like environmental benefits. The land use practices improve, which can help decrease soil and land degradation. Socioeconomic benefits, better drought management, including preparedness, response, and recovery. Reduces high costs related to post-drought rehabilitation, improves network connectivity within local communities. And there are some opportunities. This technology is important for climate change adaptation efforts in many countries because the occurrence of severe droughts will be predicted, and this will help us to assess risks and vulnerabilities and improve preparedness for drought disasters. Threats will be minimized, and expensive relief efforts following such an event will be avoided. An early warning system can give sufficient lead time, up to a few weeks, to local decision makers to mitigate drought threats. Technological advances allow citizens to receive warning system data delivery on their smartphones. We use US Drought and Meteorological Dataset on Alibaba Cloud TIANCHI website. We predict US drought levels based on meteorological data, potentially leading to the generalization of US predictions to other areas of the world. There are 6 levels of drought. Each entry is a drought level at a specific point in time in a specific region, accompanied by 18 meteorological indicators such as wind speed, humidity, temperature, and so on. The dataset has been split into 3 subsets: 47% train, 10% for validation, and 43% for testing. So here is our production pipeline model on Alibaba Cloud. Some data sources of system could be meteorological data from IoT platforms, satellites, climate apps, and data from meteorological stations. We collect and ingest these data into our drought forecasting application on Alibaba Cloud architecture. The ingested dataset will be stored on OSS. We will use a managed security service to optimize and security protection for our application and business. In order to execute ETL processes and to ingest transformed data, we use machine learning platform for AI service. Elastic MapReduce service, which hosts Hadoop and Spark on cloud, used to perform ETL processes for the machine learning job. We will use Pi, data science workshop service, and SDK API call for the following items: training and evaluation model, DSW of Pi and OSS API PyTorch for training the model. We will use a built-in EAS CMD client on DSW service to deploy and test our trained model, and Cloud Monitor service to monitor our business application. Elastic Algorithm service will be used to load and deploy our model as a RESTful API and to call the API by sending HTTP requests. EAS enable us to provide auto-scaling and blue-green development for real-time forecasting response. This real-time response enables our clients such as agricultural, governmental, and environmental organizations to make their decisions as soon as possible by gaining significant information from our drought forecasting application. We will use Quick BI service to present a real-time dashboard analysis of the drought forecasting application. This contains visualizations such as heat map, world map, charts, and guidelines. For drought level prediction, we deal with an ordinal classification problem where each drought level exists on an ordinary scale where only relative ordering between different levels is meaningful. D levels are based on Palmer Drought Severity Index. The proposed previous models suffer from a couple of drawbacks. Firstly, they cannot model the nonlinear relations and functions underlying the real data. Secondly, they don't make any difference between the exogenous input terms. Lastly, traditional RNNs suffer from the vanishing or exploding gradients, which prevent capturing the long-term dependencies. We will take an innovative approach to deal with this problem. We exploit two-stage attention-based recurrent neural networks to address the issue of selecting the relevant driving series and capture the long-term temporal dependencies. There are two main ways to approach these types of problems. One, treat it as a regression problem, or two, treat it as a standard classification problem. We will take the first approach and treat it as an ordinal regression model by mapping the class labels in -1 to 1 intervals, as you can see in the figure. For example, the drought class D1 and D2 are mapped to -0.2 and +0.2 respectively. In this approach, different levels of the target values are mapped to a real valued subspace which prevents their order. In our problem, we have mapped different drought levels into 6 discrete real values, ranging from -1 to 1. We have adopted this range in order to avoid saturation in activation function, which is linear between -1 and 1. The inverse mapping, that is from continuous value to class labels, we need to decide based on the intervals, which are shown by function f(x) in this slide. As you can see, depending on which interval the predicted value resides, the class label is chosen. Now the problem boils down on choosing the proper values of the threshold. We can use the Bayesian decision theory to help us in deriving the appropriate thresholds. After some algebraic calculations, the threshold can be boiled down to one simple equation. As you can see in this slide, the TP loss can be derived based on the empirical frequency of the class labels. The sigma can be assumed in a way that deviation is not enormous, which is valid in our model. The TL is the loss ratio by which we can dictate a proper risk policy. For example, if based on our policy, the loss of missing severe drought D4 cost us $6 more than the less severe drought level, we can enter the loss ratio as 6. In the first stage, we introduced an input attention mechanism to adaptively extract relevant driving series, aka input features, at each time step by referring to the previous encoder hidden state. In the second stage, we use the temporal attention mechanism to select relevant encoder hidden states across all time steps. With this dual stage attention scheme, our model can not only make predictions effectively, but can also be easily interpreted. This is the graphical illustration of the dual stage attention-based recurrent neural network. The input attention mechanism computes the attention weights for multiple driving series x1 to xn, continued on the previous hidden state ht-1 in the encoder, and then feeds the newly computed xt into next stage, the encoder LSTM unit. The temporal attention system computes the attention weights beta t based on the previous decoder hidden state dt-1 and represents the input information as a weighted sum of the encoder hidden states across all the time steps. The generated context vector CT is then used as an input to decoder LSTM unit. The output YT of the last decoder LSTM unit is the predicted result. And here are some future perspectives of our rate forecasting system. Lastly, let's see the demo presented by my teammate Homayun.
Hello, this is Homayun, a member of Fortune Teller team, participated in Global AI Innovation Challenge Series 2021 Intelligent Weather Forecast for Better Life. A little bit about me. I am an ML AI specialist on the cloud technology who enjoys implementing ML models and AI architectures on the cloud technology. We are forecasting the drought level by using the open data offered by the NASA-powered project and the outsource of the US Drought Monitor. We have already used Alibaba Cloud Services for implementing our AI architecture on data science workshop development environment. As we can see, we have trained model file and predicted file have already implemented on DSW development environment. I have enjoyed working on DSW due to its flexibility, scalability, and reliability. In the future, I would absolutely run our application for forecasting the drought level by using Alibaba services such as compute resources, data storage services, analytics services, and Pi platform for artificial intelligence services. We used SuiteWiz function to get a comprehensive exploratory data analysis (EDA) processes. As we can see, the features with their plot distribution and their statistical analysis here. For example, we can see max, minimum, median, average, quartile, and etc. If you select one feature here, you can see other valuable information on the right side. On the right side, we can see the association values of each feature with the other numerical features, independent variables here. And besides, we can see the association values of each feature with their dependent variable, target variable class here. For example, I selected PS feature, and as we can see, the association values of this feature with the target variable is 0.16. Besides, we can see the associations and correlation matrix in a very interactive figure here. As we can see in one glance, we can see all the features and compare their association values with each other. Now we will walk you through a demo via a web application designed by Flask framework in Python in order to present an API call for our AI-based system for forecasting the drought level. As a start, the page is shown up and takes 3 values to perform prediction. The first value is an integer, indicates the FIPS, which is a location indicator. The second is the date till which the user wants the prediction to be performed. The loss ratio is spread by the user based on the amount of the risk related. After providing all the necessary information, the prediction and the application uses the model train to cast a forecast for the days up to date specified. We have already created a GitHub profile for our team, which is called Fortune Teller Team. We also created a repository in GitHub under the name DARNN for drought forecasting. In this repo, you can find all the relevant code scripts for model training, data, web application here. We also provide a short README file for the quick overview about our work here. As an example, the notebook Jupyter includes all the code for training the model, including hyperparameter adjustment and validation. You can find all the relevant libraries, functions, and data loader which are necessary for training the model here.